Hello, let's continue with Module 6 on continuous random variables. In the last part, we looked at the uniform distribution, and now we want to turn our attention to the normal distribution. We've already talked in earlier modules, I believe, about what a normal distribution looks like. It's sometimes referred to as a bell-shaped or mound-shaped distribution. It tends to be perfectly symmetric with the mean in the middle. Why do we care about the normal curve? Well, it turns out that many things in the real world come close to this general shape when people look at their distributions. People's heights, IQ scores, other measures of intelligence like SAT scores, measurement errors turn out to be often normally distributed. In fact, I suspect that's where it got the name the normal curve, because it seemed to be a very normal shape for a distribution. A few little points about the normal curve. The mean, the median, and the mode, remember, on a perfectly symmetric distribution with one peak are all the same. So right in the middle of the distribution is the mean, the median, and the mode. As we've already said, it's perfectly symmetric. The standard deviation determines the width of the curve. We'll take a look at that in a moment. Total area under the curve is 1 unit to make it a legitimate density function. And remember that probabilities are going to be given by areas under the curve between the points we want to look at. Here's a formula that I'm happy to tell you don't really need to know, but this is the formula that mathematicians have found would trace out a perfectly symmetric normal curve with an area of 1 unit. F of x is 1 over the square root of 2 pi sigma e to the minus x minus mu squared over 2 sigma squared. But like I said, you'll be happy to know that you won't have to use that formula. Remember, the mean on a normal curve can be any number. We could have a normal curve here with a mean of 20 or a mean of 25. The mean just defines the center point of the distribution. So the mean could be anything. The standard deviation determines the width of the curve. A smaller standard deviation tends to give you a narrower, more peaked curve, and a larger standard deviation gives you a flatter, more spread out curve. Now, as with uniform distributions earlier, we want to find the area under the curve over some desired interval. Unfortunately, we can't do what we did with the uniform distribution, where we were able to just take height times base, because we just had a rectangle. The normal curve is not a rectangle. And as we discussed before, we don't want to require calculus to find the area under the curve, but fortunately we won't have to do that. Fortunately, we'll be able to give you a table that shows you the areas of one particular normal curve, and then you will be able to transfer or translate any other normal curve to that curve and find the area you want. The one normal curve that we're going to work with is sometimes called the standard normal, or Z distribution. Remember in earlier modules, we had the formula for Z values. Z is just x minus mu over sigma. As I pointed out then, what Z really does is it takes a variable x with some mean mu and some standard deviation sigma, and it converts it to Z. And Z is simply going to be a variable that has a mean of 0 and a standard deviation of 1 unit. So the standard normal curve is just a normal distribution that sits on a mean of 0. Every 1 unit is a standard deviation. And most textbooks have a table of normal distribution probabilities based on the Z curve. And once we learn how to read that table, we'll be able to find normal probabilities. This is just a picture of the standard normal distribution. As I said, it's just a normal curve that sits on a mean of 0, and it has a standard deviation of 1 unit. Every 1 unit represents a standard deviation. Notice, of course, if the mean is 0, half the probability is above the mean and half is below the mean. It's important, before we take a look at the table in a minute, that you do not confuse Z values, which are values on this axis, with probabilities, which are areas under the curve. These are different things. Z values can be any number from positive infinity to negative infinity. Although we'll see that most Z values are in the range of roughly 3 to negative 3, because remember, 3 would be 3 standard deviations above the mean, and negative 3 would be 3 standard deviations below the mean. And if you remember our discussion of normal curves earlier in the course, most of the time you're within 3 standard deviations around the mean. But Z values can actually be any number. Probabilities under the curve, remember, probabilities range from 0 to 1. So they can't be any number. Don't forget that Z values can be both positive and negative. A positive Z value simply indicates you're on the right side of the distribution here, you're above the mean, and a negative Z value indicates that you're below the mean. Now, in a minute, we're going to take a look at a cumulative Z table that is often in most textbooks. In fact, many textbooks these days give 2 Z tables. Let's go back to our previous slide. One for the positive side of the distribution and one for the negative. Some books just give one table for one side because you can figure out the other side by symmetry. But we're going to work with 2 Z tables. The Z table will have 2 parts to it. Let's look at a sample portion of a Z table. This is part of your cumulative standard normal table. Down the left-hand side and across the top are Z values. Across the top allows you to go out a second decimal place. In the middle of the table here are cumulative probabilities. Remember, a cumulative gives you all probability less than or equal to a point. So for example, let's say I looked up a Z value of 1.24. You go down the left column till you get to 1.2, go across the top till you get to 0.04, look at the cumulative probability you have here, and the cumulative probability is 0.8925. That's basically telling you that the probability that Z is below 1.24 is 0.8925. And if you know that, you also know the probability that Z is above 1.24, because these two have to be complements to one another. Just take 1 minus 0.8925 and you'll get 0.1075. And again, this is all explained verbally back on this slide. Look up a Z value like 1.24, and the table is going to give you the cumulative probability below that Z value. We could then find areas above it by simply subtracting from 1. Again, as I reminded you earlier, it's important not to confuse Z values and probabilities, especially because notice in this table some Z values are less than 1 themselves. For example, we have a 0.8 to 0.9 here. Those might look like probabilities to you, but they're not probabilities. They are Z values. Let's do some practice so that hopefully now you understand what the table gives you. Let's find some probabilities on the normal table. And by the way, later we'll be showing you how to do all of this on your calculator if you have a TI-83 or 84. But it's always a good idea to be able to use the tables as well, just in case your calculator batteries die or something like that. You need to be able to find the answers in a different way. Supposing I wanted this probability, the probability that Z is bigger than 1.42. Look up the Z value of 1.42 in your positive Z table. Now remember, the table is going to give you the cumulative probability below that. And if you look in the table, it's going to tell you that probability is 0.9222. But that's not what I asked you for. I asked you for the probability that Z is above 1.42. I want everything up here. So we'll simply take the cumulative in the table and subtract from 1. Take 1 minus 0.9222 and you'll get 0.0778. So the probability that Z is greater than 1.42 is 0.0778. Let's look at the second one, which is a little more complicated. Now I gave you two z values. I want the probability that z is between negative 1.2 and positive 0.84. So positive 0.84 is up here somewhere to the right of the mean. Negative 1.2 is somewhere down here to the left of the mean. And I want the area between those two. You should be able to see that if I look up the z-value of 0.84 and get its cumulative probability, everything below it, and then subtract off the cumulative up to negative 1.2, I will be left with the area that I desire. So that's exactly how you'll solve for this problem. Look up 0.84, you'll get a cumulative probability of 0.7995. Look up negative 1.2 and you'll get a probability of 1.1151. Subtract that from the first one and we get a probability of 0.6844. So the probability that negative 1.2 is less than z is less than 0.84 is equal to 0.6844. The third one here should be fairly easy. We want the probability that z is less than 1.96 is equal to 0.9750. Excuse the fact that I forgot a parentheses in there. If you just look up the z value of 1.96, we wanted all probability below it. That's exactly what the table will give us. So look up 1.96 and the table will give you the 0.9750 here. Finally, our last one is similar to the second one. Supposing I want the probability from 0.5 to 1.5. I want the probability that z is in between those two. Again, here's 0.5, here's 1.5, and again, we can find this by using subtraction. Take the cumulative below 1.5, subtract the cumulative below 0.5. When you do that, you'll get a final answer of 0.2417. Okay, on these problems, I gave you, let's go back for a second. I gave you these z values and had you find a probability. You should also be able to do it the other way around. If I give you a probability, you should be able to find a z value that satisfies an equation. And that's what we're going to do next. I refer to this as working backwards on the z table, because we're going to have to do things a little differently. Instead of looking up a z value and getting a probability, we're going to have to look up a probability in the table and get the correct z value. Let's do an example first. We want to find a z value which we're going to call z0 such that the following probability holds true. The probability that z exceeds z0 is 0.025. If you look at that equation, it's basically saying, find me a z value, which we'll call z0, such that the area under the curve, at the area under the z curve, to the right of that point, is only 0.025. It's a good idea on problems like this, again, on all of these problems, to draw yourself a picture. First, we should realize that the z value that we're looking for has to be in the upper end of the distribution. Why? Because you have a very small probability above that z value. If z0 is down here, if it was a negative value, you'd have a very large probability above it. But 0.025 is a very small probability. So the z value we want is up here somewhere, such that the area above it is 0.025. Now remember the table in the back of the cumulative probability table that you have access to in the book is a cumulative table. It gives you all probability less than a point. So if 0.025 is above that point, 0.975 has to be below that point. So go to your table and find a 0.9750 in the middle of the table, or somewhere in the middle of the body of the table. Look at the row and column you're in, and that'll give you the z value that must be associated with that. In this case, that z value is 1.96. So the probability that z is below 1.96 is 0.9750, which means the probability above it is 0.0250. So the desired z-value was 1.96. Let's do a couple more practice here. I'm going to do the first two, and then I'm going to leave the last two for you to do on your own and practice with. Again, number one here, we want to find a z-value such that the probability that z is above z0 is 0.1587. This one is fairly similar to the last one. 0.1587 is a fairly small probability, so it has to be in the upper end of the distribution to have that probability above that z-value, or rather to have the probability that z exceeds z0 to be 0.1587. Z0 will have to be in the right end of the distribution. Again, if Z0 was down here in the left hand, you'd have way more than 0.1587 above it. With 0.1587 out here, subtract that from 1, that means the cumulative probability below it has to be 0.8413. So go to your table, your positive Z table, find a value in the middle of the table of 0.8413, look at the row and column you're in, and you should get the Z value to be 1.0. So the probability that Z is above 1.0 is 0.1587. I know this wasn't drawn to scale very well there, and I apologize for that. This looks a little bit larger than that. But imagine it was a little smaller. Let's do one more. This time, let's do one that's on the left side of the distribution. Suppose we want to find Z0 such that the probability that Z is above Z0 is now a very large probability, 0.9798. This means that almost the entire distribution has to be above that z-value. If you think about it for a moment, that means that that z-value has to be on the left end of the distribution in order to have a large probability above it. With 0.9798 above it, we need the cumulative below it again before we go to the table. Subtract the 0.9798 from 1, and you'll get 0.0202. That has to be down here in the lower end. So now go to your negative Z table, because we know we're in the left end of the distribution. Find a probability in the table of 0.0202. Look at the row and column you're in, and you should get this Z value of negative 2.05. So the probability that Z exceeds negative 2.05 will be 0.9798. As I said, I'm going to leave these last two for you to do on your own. The answers are on the next slide, so if you don't want to see them, you might want to stop the recording right now and work on these for a while, and then you can come back later to get the correct answers. So work on those two. If you're having any difficulties with them, send me an email, and I can explain them to you more thoroughly. So we're going to go to the next slide now, but like I said, if you don't want to see the answers, you could stop the recording now. So this is the end of part 2, and in the next part we're going to move on to solving normal distribution problems.